Welcome back. This is Dr. Me at the Actuarial Academy, and we will work a bank investment problem where the account earns an annual rate R that's uniformly distributed from 0.05 to 0.1, and the initial value of the investment was 8,000 units, and after compounding the interest continuously, the value after 1 year, of course, is given by 8,000 times e to the r, where v is also a random variable, and we would like to derive its CDF. So clearly the reason v is a random variable is because we just said that r is also randomly distributed, the actual annual rate. So v, therefore, a transformed random variable with the transformation given as follows. So we'd like to find the CDF, f of v, where v satisfies this constraint. V is strictly between 0 and 1. And really the only reason why they do that is just to make sure the problem statement's clear, that we're really only solving for the CDF where things are actually interesting. So as I always provide a couple of facts to help facilitate the successful completion of these problems. And so what you'll need to know for this problem is the CDF of R, the CDF of the uniform random variable. We'll find out later that we actually need this to complete this problem. So the CDF is a probability that R is less than or equal to R. It stands for cumulative distribution function. It's equal to F, and just to be very clear, F of R, big R, R. So this is the cumulative distribution function of the uniform random variable, and it's given as follows. So it's easy to memorize. It's 0 for values less than the lower end of the support, where the lower end of the support is 0.05, and it's 1 for above that support, but in between 0 and 1, between 0 and 0.05 and 0.1, that is within the support, it's basically the variable minus the initial point minus the difference of the endpoints. 0.1 minus 0.05. So again, it's easy to memorize. It's good to have in your back pocket, ready to be pulled out at any time solving these problems. We also need some algebra facts. Don't let algebra get in the way of or preventing you from successfully getting a problem correct. So the natural log of a times b is the natural log of a plus the natural log of b. The natural log of a divided by b is the natural log of a minus the natural log of b. And we also have the natural log of e to the r is equal to r, so the exponent actually comes down times the natural log of e. Natural log of e is 1, so this just equals r. Now, again, these are rules that are specific to this problem. Okay, so I'm not trying to teach you algebra here, just trying to say exactly what's unique or specific to this problem. Okay, so we need to find the CDF f of v, and so we'll just apply a definition here. F of v is equal to the probability that v is less than or equal to some little v. Okay, well, this is precisely what we're looking for, the CDF. This is the CDF of v. Okay, so now you follow standard steps and just substitute this for v here. So this just becomes 8,000 e to the r, then is less than or equal to little v. Okay, now the strategy is to solve for r, and this is where we'll use our fact 2 and use the natural log, because we use the natural log to bring down the exponents. So I'm going to go ahead and skip a few steps, and if you don't mind, understand that this is the natural log of 8,000 plus r. Okay, basically times the natural log of e, but we already know that equals r from up there, so I won't repeat that, and that's less than or equal to the natural log of v. Okay, so this is then equal to the probability, and I'm going to go ahead and solve for r here, is less than or equal to the natural log of, and again I'm going to skip some steps here, so if I were to write this out, that would be the natural log of v minus the natural log of 8,000. Okay, but I'm going to go ahead and employ this identity here and just write that as natural log of V divided by 8,000. Again, I don't want to bore you with details of algebra. But look, lo and behold, we've reached an interesting milestone here in that this is now the CDF of our uniform random variable because we've isolated R. But it's evaluated at the natural log of V over 8,000. Okay. So just for clarity, let me write down exactly what I just said. This is then equal to F of R evaluated at the natural log of V over 8,000. Again, don't let the math or the complexity of this or the syntax scare you. This is just basic. We're evaluating F of R at natural log of V over 8,000. So this is then just equal to, and we're only really interested in it for V between 0 and 1, which essentially means we're going to evaluate it at R here, this value here. So then this will just be equal to the natural log of V over 8,000 minus 0.05. Okay, so I'm actually evaluating this CDF of our uniform random variable at R with this quantity, natural log of V over 8,000. So R here becomes natural log of V over 8,000 minus our 0.05, all divided by 0.1 minus 0.05, which is just 0.05, right? So we're actually done right there. But a lot of the actuarial problems don't give it to you in this form, so you need to simplify it in the form they actually give it because it's multiple choice. Well, we can pull out this 0.05, so 0.05, 1, and think of it as 1 over 0.05, which is nothing, which is 20, and then times the natural log of our V over 8,000. And then we still have our minus 0.05, which is the final answer to this problem. Again, this is the CDF of V, where we're only interested in where V is strictly between 0 and 1, and this is where this is the valid CDF for V strictly between 0 and 1. Thank you very much.